All right, kiddos, here we go on section 11.3b. Hope you guys are doing well. Hope you're keeping track okay. I have a lot of you that were really confused about Google Classroom, and so you were asking me a lot of questions about Edpuzzle and posting and pictures. And remember, I have posted in your Google Classroom some troubleshooting tips. I also emailed them out to you and your parents yesterday, just in case if you couldn't understand what I was advising, maybe parents could help you out. Maybe you weren't using a computer or laptop, but you should be, at least not for everything, but at least for posting, it should make it a lot better for you. So just trying to kind of make your lives a little bit easier as far as technology, but feel free once again to reach out if you guys are getting stuck. But here is the last part of section 11.3b, okay? Basically, the biggest thing that we're talking about in the second half of section 11.3 is comparisons, comparing data distributions, okay? So we're going to have not just one, what are these called again? These bar graphs that show the frequency, histograms. Not just one histogram, but two. Not just one collection of data, but two. Probably, roughly at least, measuring the exact same thing. Like in this one, the context is text messages for the example that's coming up right here. And how frequently male students or female students use emoticon for your emojis and all that jazz. However, even though it's a similar context of what is going inside text messages, we're measuring two different populations, one male, one female. So just kind of giving you an idea of what some of these comparisons might look like in the sense of in these directions in this example in the book. And I'm just using these examples because you guys can reference them, look at them, and look over them. But it does say compare these distributions using their shapes and appropriate measures of center and variation. So technically, the nice thing is that this really is giving us what to look at and what we should be using, etc. For some reason, my screen kind of froze. So let me go ahead and try one more time to see if the iPad's going to share. If not, I can just throw it under my webcam and we do it that way. But once again, at the bottom of this first paragraph, it talks about, there we go. Let's see if it works this time. Comparing the distributions using their shapes and their appropriate measures of center and variation. So we have this one in the book that you guys could definitely look at and you could compare to, but I'm going to go ahead and pop over to a new example where they're asking basically the exact same thing. And the nice thing is once again, they're very detailed in their language as to what they want you to do. They want you to compare using their shapes and appropriate measures of center and variation. I'm going to go ahead and underline those, the shapes, and then the center and variation. And that's something that we talked about in 11.3, the first part. So looking at these two shapes, I hope that you guys can see which one looks more symmetric. They are both a little bit off. Neither one is perfectly symmetric, but there definitely is one that seems more symmetric. The one that seems more symmetric in my mind is going to be the city B. City B is approximately, we can use that, because it's not perfectly. If I was to cut this right down the middle, and I'm not sure exactly where right down the middle would be. Somewhere here-ish, I'm kind of just guesstimating. But somewhere down the middle, I know it's not exactly the same on the right and the left, but the data does seem pretty centered right here in the middle, with some tapering off on this side and some tapering off on that side. That end, I would call city B roughly symmetric, but not city A. So city A, if it's not symmetric, it would be skewed. And if it's skewed, what type of skew would it be? Think karate kick. If you're karate kicking out your leg and the majority of your body is moving the other direction, which way are you kicking? In this one, hopefully you realize you're kicking to the right, with the majority of the data being over here on the left. So that's going to be skewed right. Now, thinking about both of those, okay, I have one that's symmetric, I have one that's skewed right. How does that shape tell me what would be the best measure of center and variation? You might need to go back to yesterday's video or back to yesterday's homework or notes that you hopefully were taking down. Remember, you can use notes and books and calculators on quizzes and tests during this time, so that might be a really big motivation for you to be taking notes and writing down examples. I have symmetric and I have skewed right. Okay, hold on. So, oh, that's right. Whenever I have anything that's symmetric, I'm going to use the word therefore. That's a good connector word. Therefore, because of the shapes, because of that symmetry, because of the skew that's to the right, therefore, city B, his center and variation, we can almost put both of those, and then we're just going to go ahead and answer, okay, well, what is the best thing for his center from yesterday? If it's symmetric, that basic shape, and we're going to call it a bell curve in just a second, if it has that basic symmetry, we can say the mean and the standard deviation are great for measuring those two. Going back to section 11.1, back to the beginning, those are the two that would measure the shape and the center and variation. However, for my next one, I'm going to put while city A, for very different reasons, but similar in that we're looking at its shape and seeing the skew. For similar reasons, but with a different shape, city A, his center and variation. If you guys remember, if it's not mean and standard deviation, what's the other option? Instead of mean, the arithmetic average, it's going to be middle. And middle, snazzy name for that is median, like median in the road. And instead of standard deviation, like on standard, how much it differs, which is kind of actually shown in each of these graphs by how wide the bars are. How wide the bars are kind of give us an idea of the standard deviation. But if it's not standard deviation, it's going to be the what's that called? The 5-number summary. We're talking about the 5 most important numbers of, the 5-number summary, the 5 most important numbers in a box and whisker plot. Now, if they wanted us to go more in depth describing the comparison between these two, there is one other thing that we could say. The directions don't specifically say it. I'm going to zoom in over here. What's one other comparison that I could make? Well, this is talking about monthly precipitation. Precipitation is kind of like rainfall. So monthly precipitation, I could see the majority of data, or the majority of, what are we talking about? Precipitations, oh, in a month. Sorry, I missed the monthly up there. In a month, the majority of city A's data is on the lower end between like 0 and 11-ish, whereas the majority of city B is up here in this range. I could say city B has a higher typical monthly precipitation. I can totally use, I was going to try and change the words, but why not just use the words that they give us? I'm just going to say precipitation. Looking at this data, since city A, since the majority of its data is, or the majority of its precipitation is over there on the left, and city B is mostly on the right, city B is on average or generally going to have a higher typical monthly precipitation just because that's where the data is. But something else that we could say is that city B, since it is more standard or more symmetric, more like that bell curve that we're going to see in just a second, we can actually also say, but in city B, the months tend to differ more. So it has more variation. It does have a higher typical monthly precipitation. A normally has a lower, and not only does it have a lower, the months are also more grouped together because of that skew, whereas in city B, it's more spread out. Anyway, just a couple ideas of things that might be helpful in homework. However, there's another type of comparison that I want you guys to see. What if they were to give us a table? Now, this isn't necessarily a frequency table, at least not clearly. It is a table of data. It's given to us tabularly. But if they give us tables, that's going to be kind of similar to example 4 down here. Now, before we get to example 4, there is something that's really, really, really important for statistics. It's not something that we necessarily have to memorize at this level with what we're doing. But this chart is actually something that's really important in statistics when talking about what we call the normal bell curve or the standard bell curve. Some of you might have heard of that before, some of you might not have. But the standard bell curve is a very important measurement in all of stats. And so that bell, you might think of like, why is it called a bell? That might be a little weird, but some of you are like, no, if you put a handle on it, like, yeah, it looks like something that you could ring. Not perfectly because it has this weird like tapering off at the end, but in these standard bell curves, if something is roughly symmetric, we kind of know, now remember, this weird guy, lowercase sigma, was who we talked about before as being standard deviation. The guy that we found with that big old chart of data from section 11.1. So this lowercase sigma guy, he's standard deviation. I see him in this chart. And if you notice, here's my good old fashioned X bar, my good old fashioned mean right here in the middle. So with my good old fashioned mean right here in the middle, if you guys are noticing, what we're doing is we're moving out by standard deviations. So we're adding 1 standard deviation, 2 standard deviations, subtracting 1, 2. That's kind of why I showed you guys the width of these bars kind of go together with this idea of a standard deviation. I don't want to go too deep or too heavy, but what I do want you guys to see is that with these standard deviations, there is like a typical or a rule behind these standard deviations that is generally true. Technically, there are decimal places that make this way more precise, but we're just going to say about 68%. We're not going to need to go into decimal places, but about 68% of data. Now think, box and whisker plots, there was 25% of the information or of the data quantities in each of those places, the whisker before the mean, after the mean, and the other whisker, or remember the box held 2 of those, that was 50%. That's how much data there was. When we're not specifically doing a box and whisker plot, we can also look at these, one of these kind of like standard bell curves is what we call them again. And we could say, okay, if you go 1 standard deviation away from the middle, 1 to the right, 1 to the left, if you go 1 out, you're going to have about 68% of the data. I'm going to try to get my iPad back in. It wasn't very happy. Let's see if we can reconnect. But 68% of the data, it's not quite 78%. My screen sharing is paused. Let me try to go out and go back in. Nope, the Wi-Fi is unhappy, but that's okay. What we can do is we can go ahead and just get it under the webcam. A little bit annoying, but it definitely will work. Sorry guys about that, but we'll be back in just about 5, 4, 3. Let me move my hydro, 2, and there we go, 1. Okay, let me try to zoom in just a little bit. Let's hope that the webcam can at least kind of focus on what it needs to. Okay, with the standard deviation, we have 68% that's falling in between 1 on either side. So right here in the middle of the standard bell curve, that's going to have about 68% of our data. It's not that nice 75%, but it's still a lot. It's still a majority. And then if we were to go out 2 more standard deviations, I should say, I apologize, 1 more standard deviation on either side, a total of 2. Then we would go ahead and 3 again. If we kept going out even wider, then we would have 95% of our data, the majority of our data, which is why I was able to go to this I saw as a more symmetric diagram. And I was able to say, you know what, I know that there are some over here, but man, the majority of data, because if I was to know the mean, which we don't know perfectly, not from this picture, they don't really show it to us in a histogram, but we can estimate, we can guesstimate where the mean would be. If we were to go out 1 standard deviation, 2 standard deviations, man, 95% of that data, that's way higher than the majority of the data down here in City A. Coming back. That's something that's super important for statistics as far as this bell curve and this symmetric distribution of data. They basically say any data values that are beyond 2 standard deviations from the mean. And you might hear this in kind of everyday language if you start listening for it about standard deviations, 1 standard deviation, 2, especially if you're listening to some sort of movie that has to do with stats. But they're saying anything outside of that 95%, anything outside of those 2 standard deviations, so anything here on the tails of the curves, they're considered unusual. Kind of like an outlier, but an outlier is like 1 specific way out, kind of like the baby gorilla, how the weight was so much different, or in your homework. I think I was commenting on one of your guys's homeworks that you got stuck on it wasn't a gorilla, what was it? A bear? Panda? Oh, I don't remember, some animal, an elephant maybe? Anyway, you guys had something similar. An outlier is like, whoa, 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 everything is pretty normal except for this guy. This guy's way out there in Timbuktu. Which is an actual city, by the way. But coming back, They're just called unusual if they're outside that normal 95% of data. Okay, I just wanted to show you guys that because it is important in stats. We're not going to spend a lot of time on it, but it might be kind of helpful just to kind of know in the back of your mind and to have this idea of standard deviations being kind of like these bar widths from, if it was symmetric, from the very middle, which is where the mean would be. But as soon as it's a little bit skewed or it's not perfectly symmetric, the mean moves just a little bit. Let's check out this example real fast before we go ahead and do our own, and then we're done. So once again, we're comparing two different types of data. And this one we're talking about survey of how many pairs of shoes they own. So surveying men, surveying women, and comparing the two and the responses of the two. Now, remember when we're making box and whisker plots, we need to know the lowest and graph that, the highest and graph that. The first quartile, graph, third quartile, graph, and the mean goes in the middle. And then we draw our box and whisker plot, and then we can start answering questions about it. So this one has already been drawn, and once we have these different box and whisker plots, we can use them, and we can talk about things like the shape of this one being skewed to the right because that right whisker is way longer. This one being symmetric because they look about the same. We can also talk about the spread, how the spread of the women, that's way more spread out, meaning women tend to differ way more on how many pairs of shoes they do or how many pairs of shoes they own than men do. Men seem to be, yes, on the lower end of how many pairs, but also the data is more grouped together and that men are more similar, seemingly from the poll anyway. We can talk about other comparisons as far as, that's what I just kind of said, that women, look at this, 75% of women have at least 12 shoes, if not all the way up to 24 or more. So 75% of women have at least 12 shoes, whereas 75% of men have at most 10. So that's a very different result, right? But we also have something where it asks us, hey, can you actually estimate or guesstimate between 10 and 18? Okay, that's here to here, a little bit above that quartile, and then it's a little bit below. Well, I know that's 50%. I don't know, maybe 60, maybe 70. We could kind of guess. Some of this is going to be guesstimation based on what we know, and some of this might be just simple facts. Let's go ahead and see with our example, a blank one. I've already made the number line just looking at the data. So they're not giving us all the different survey results because they've surveyed 50 different people. I don't want all the responses from 50 different people. I want someone to have looked at those polls and then summarized it into something like a table like this, where I see something like, first of all, I see something helpful. Max. Actually, in section 11.2, I made these green as well. All right, but min and max. For females, I see the minimum. I'm going to use the yellow one at 16. So if I turn it on here and make a minimum mark at 16 for females, and then I go to, let's see, 40. So I come up to 40. There we go. For males, I'm going to go ahead, sorry, make it kind of complicated. For males, I'm going to choose blue. For males, I have the lowest at 18 and the highest at, we're not talking about teams anymore. We're talking about how many hours a week, a little bit more on a level playing field. Guys, the lowest of theirs is 18 and the highest of theirs is 52. Oh man, that's the opposite. Based on how I wrote. Now we can't stop in the max. I mean, we have to start there with the lowest and the highest, but we have to get those quartiles down. But the nice thing is, keep looking. We have the quartiles, the first quartile and the third quartile, and then we have that median right there in the middle. So the first quartile for females is going to be at 24. The third quartile is 32. I have 24, with the median being at 28. Now, if you know how your box and whisker plot goes, we actually have enough to make our box and whisker plot right now. And goes out to these edges. It helps to make these points a little clearer. But there's our box and whisker plot for females. Now for males, let's get the rest of the information in as far as the first quartile is 30. So third quartile is 46. And then that center, that median is going to be 38. There we go. So at this point, I can go ahead and follow my boxes as well. Trying to be really obvious on the key points. There's the mean, this quartile going out. There we go. Okay, so we have both of our box and whisker plots. Now there's a couple things you guys should be able to see right away. Like if I was to ask you which one is more spread or which one has a higher spread, hopefully you guys are like, oh yeah, the males for sure. Meaning the females are more grouped together, more similar as far as the people that they polled, but the males were way, at least had more variation and more variability in their answers. And we can see that from the box and whisker plot being more spread out. I could also think about, if I'm looking at these boxes, 75%. Most of the males listen to at least 30 hours of music. However, the females, okay, well, the females also, most of them listen to almost 30 hours. They're more around 24 hours. Most of the females listen to at least 24 hours. But if you notice, it's not just 24 till forever, it's 24 to this one's only 40. So we could say on average for we'll listen to more hours of music I know my voice kind of trails off when I face the webcam, so I went ahead and just finished writing them and I talk through it. So from this, I can see that a typical male is going to look at all these males up here that are higher than most of those females. So we have on average kind of, or a typical male listening to more music or more hours of music than a female. But we also have this extra characteristic that since this data is more spread, we can also say that males differ, or there's more variability in the number of hours that a male will listen, in the sense of there's more, the data is more spread out, or they're going to differ more from each other as far as like just asking two random guys, man, they could be on two totally different spectrums as far as how much music they listen to, whereas females are more grouped together. Now, letter C, it asks us another question about how many females surveyed would you expect to listen to music between 22 and 34 hours? So 22 and 34 you notice that entire box is in that range, and so that entire box is 50% of the data, the entire box. We also have a little bit more. So you guys could say 50, do more than 50, 60, probably not 70, because remember, 75 goes all the way to the outer edge of this whisker. I think maybe like a 60 or 65. Now, hold on. They said how many? Well, I mean, I guess in this context, they only surveyed people. So I guess we could say for this survey, we would take 60% of 50 or 65% of 50 and get that actual number. But for my purposes, I think us saying 60 or 65% of the data is sufficient as far as getting the idea across. If we were to keep on looking, I don't know if they have any other questions for us. Oh, they do. They have one more. That last question says, if you survey 100 more females, so like beyond this poll, if we're trying to predict what's going to happen if we go out and survey more, and this is something, guys, especially with an election year coming up, that remember, they can only poll so many people. There's this thing called the census that's happening right now, and that might be a bit bigger deal. But a lot of polls that they do where they survey people, they're just surveying a certain number. Now, the more people they survey, theoretically, the better idea of the results they might have. And what I mean by that is a lot of surveys are trying to predict or give people an idea of how they're doing or how things are going, or what is the conclusion or result that they could assume is going to happen. From everything like products and whether people like products to movies. We live really close to Hollywood, and they have like practice or sample audiences to try out movies and sometimes change endings and things depending on how people react. And a lot of this is just trying to predict and to try to be as successful as possible and change or adapt based on how people are stating their opinions. But they have to only poll certain numbers of people and then make a prediction. So this one says, all right, what if we survey 100 more females? We've surveyed 50, let's survey 100 more. If these results are typical, if these results are a good sampling, and if these results will be a good prediction, okay, so then how many would you expect to listen to music between 16 and 40 hours per week? Yeah, 40 is max. Guys, that pretty much holds in the entire female population. So our guess now, does that mean that there are absolutely no females out there listening to more than 40 hours of music a week? No, definitely not. But in this sampling, 40 was the highest. So basically, absolutely all of them would fall in between that range. That'd be a little dangerous. That's what happened in this survey. But what if you survey 100, twice as many females? Couldn't there be a little more variation? Couldn't there be some females that either don't listen to any or barely listen to any? They do podcasts or something else instead, or they read like actual books, go figure. Or couldn't you have some that literally have like their headphones in all day long and are listening to music? Anyway, all that to say, okay, there might be some more variation, but what could you say? Maybe not everyone, but how about almost all. Almost all. We would expect. Now, we're not saying that it's really dangerous to say, oh, well, from this little sampling of 50, then we know for sure there are no females out there that don't listen to more than 40. No, that'd be foolish. That'd be kind of silly to say. But we can say, okay, we expect almost all, or at least most. Almost all, or at least most. To fall within that range. All right, cool kids. We've basically talked about a few different ways of comparing data. One is just comparing the shapes, and from those shapes, remember, we can make some of those conclusions we talked about yesterday. But then what else we can do is we can actually go back and review section 11.2, take data, hopefully nice and summarized for us, make some box and whiskers, think about the shapes. We didn't actually even talk about the shapes in this one. We should have probably talked about how the guys, my marks were pretty evenly apart. The guys seem to be maybe a little bit skewed left. That whisker is a little bit skewed left. The girls seem pretty symmetric, but actually they're both pretty symmetric in this example. Maybe the guys are a little bit more skewed left, but they both seem pretty symmetric. We didn't actually talk about that, but then we went on and we talked about, okay, what are some different comparisons they might ask for us to do? You guys in homework tonight, or at least for section 11.3b, whatever time of day you're listening to this, is going to be the exact same pages as before, numbers 15 and 19. 15 is kind of short, it's talking about shapes and measures like we started today. And then number 20, ooh, whatever it is, nope, number 19 is a little bit longer like the one we just did. Hope that's pretty sufficient to help you guys out. And remember, if you guys need me, I was not in math lab today, but I will be tomorrow, which is Friday. Otherwise, you can catch me on Monday. All right, guys, I'll see you later. Take care.